Hello, this is Chapter 7, homework from Chapter 7. In it, we'll be solving problems 1, 3, 4, 14, 21, 31, 33, 38, 41, and 61. Let's begin. Number 1, Chapter 7 reads, in one day, a 75-kilogram mountain climber ascends from the 15-meter level on a vertical cliff, 1,500 meters, sorry, on a vertical cliff to the top of the 2,400-meter level. The next day, she descends from the top to the base of the cliff, which is an elevation of 13 meters. So the following day, she goes to 1,350 meters. Oh, what is her change in gravitational potential energy on the first day and on the second day? So on the first day, we have mg delta h. So we've got 75 kgs times 9.8 meters per second squared. And delta h would be 2,400 meters minus 1,500 meters. All right, so we have clear 75 times 9.8 equals times 2,400 minus 1,500. We have 6.615 times 10 to the 1, 2, 3, 4, 5 joules. That's day 1. Day 2, mg delta h is, let's see, and this is negative, right? Negative. The change is negative, she's gaining energy. All right, so we have 75 kgs times 9.8 meters per second squared. She's going against the force of gravity, that's why it's negative. Times 1,500 minus 1,350. And that's going to give me 75 times 9.8 equals times. Oh, I'm sorry, this is 2,400. 2,400. And we get 7.796 times 10 to the 1, 2, 3, 4, 5 joules again. All right, that was problem 1, chapter 7. Okay, problem 7.3 reads, a 90-kilogram mailbag hangs by a vertical rope 3.5 meters long. A postal worker then displaces the bag to a position 2 meters sideways from its original position, always keeping the rope taut. What horizontal force is necessary to hold the bag in the new position? That's A. B, as the bag is moved to this position, how much work is done by the rope and by the worker? Okay, so what's going on here is you've got something like this. Oh, let me plug my cord in. You've got a rope hanging here holding 90 kilograms, right? Let's see, 90 kilograms. And we've got 3.5 meters. .5 meters here. And then we move it over here. And this is 2 meters. And this is also 3.5 meters. Oh, I was going to come. Yeah. I'm going to go shopping. Okay, 7-3. So we have the rope and the haul bag being hauled by the rope. All right, so let's go ahead and do the sum of the forces. Sum of the forces in the Y. That's going to be 0 because it's not going up or down in the Y. So that's going to be equals T cos theta, theta, and that's going to be equal to mg. And sum of the forces in the X is going to be T sine theta equals F. T sine theta equals F. Because there's a force that the postal worker is applying to that package, that parcel, to move it horizontally. Okay, so now what we're going to do is we're going to divide to get rid of T. So T sine theta equals mg. I'm going to divide the one equation by the other, and that's kind of a trick that a lot of times happens in physics to eliminate terms. F. Okay. Now what? Tan theta equals mg over F. I'm solving for F, aren't I? Let's see. I've got to solve for that. Okay, I know this is 2, and I can get that angle right there. Tan mg over tan theta equals F, and tan theta would just be 2 meters over 3.5 meters. So I could do it that way, right? Let's see. Oh, no, I'm sorry. No, that's not 3.5. It's whatever this is, which I don't know what that is. So let me just go ahead and solve for theta. So sine theta equals 2 meters over 3.5 meters, right? Because as I move this out, this is going to go like that. Okay, so yeah, it's not 3.5 anymore. So theta is going to be equal, theta equals 34.85 degrees, 34.85 degrees. So mg divided by, so F equals 9.8 meters per second squared times 90 kg divided by tan of 34.85, and F is going to be equal to, let's see, 610 newtons. All right, and that's part A. Let me get some board space now. Okay, so now we're going to do part B. So the tension in the string does no work. It's perpendicular to the motion, but the force by the worker does that mg delta h, right? Because the work done is equal to the force times the distance. So what we're going to have here is mg times, this is going to be, delta h is this, right? And that's going to be 3.5, the whole thing, minus this guy, which is 3.5 cos theta. So it's going to be mg times 3.5 minus 3.5 cos theta, which is going to be 90 kilograms times 9.8 meters per second squared times 3.5 minus 3.5 times cos 34.85. And that whole thing is going to be 5.50 joules. And that was chapter 7, number 3B. Okay, chapter 7, number 4 reads, the food calorie equal to 4,186 joules is a measure of how much energy is released when the body metabolizes food. A certain fruit and cereal bar contains 140 food calories. If a 65-kilogram hiker eats 1 bar, How high a mountain must he climb to work off the calories, assuming that all the food energy goes into increasing gravitational potential energy? All right, so let's see, we've got the food calorie is in joules. So we've got, what is it, 140? 140 calories times 4186 joules per calorie is going to be equal to mg delta H. So we've got, I'm solving for delta H. So 140 calories times 4186 joules per calorie divided by, now what did that hiker weigh? 65 times 9.8 meters per second squared. And that's going to be equal to 920 meters. And that is not on the flat. That's an elevation gain of 920 meters. Okay, that's A. If as typical, only 20% of the food calorie goes into mechanical energy, what would the answer be? So now we're assuming that the rest, the 80%, goes into maybe, I don't know, bodily processes. So let's figure what this is now. So we only need to burn 20%, so that's 0.20. And that's going to really reduce it to 180 meters. So now we're assuming that that 80% goes into, I don't know, keeping the body's metabolism or the heat, a 98.6, digesting food, so on and so forth. All right, let's see. An ideal spring of negligible mass is 12 centimeters long. So X at equilibrium is 12 centimeters. So that's going to be 0.12 meters. When nothing is attached to it, when you hang 3.15 kilogram weight from it, so mass equals 3.15 kg mass from it, you measure the length to be 13.40 centimeters. So X final equals 0.134 meters. If you wanted to store 10 joules of potential energy in the spring, what would its total length be? Okay, so I have to calculate the spring constant first. All right. So F equals KX. So F is going to be 3.15 kgs times 9.8 meters per second squared. And delta X, we're solving for K, equals, I'm going to just go ahead and divide by delta X equals K. And that's going to be 0.134 meters minus 0.12 meters. And so K is going to be equal to, let's see, K is going to be equal 2205 newtons per meter. So now K equals 2205 newtons per meter. And that's figuring out K. Now let me erase this. Now I have to figure out how to, what is it, what I'm solving for? If you wanted to store 10 joules, what would be its total length? Okay, so the elastic potential energy of a spring is given by, E potential of a spring, that's U, right? U is going to be equal to 1/2 kx squared, 1/2 kx squared. So how many joules of energy do you want to store? If you want to store 10 joules, 10.0 joules times 2 divided by 2205 newtons per meter equals x squared. I'm going to take the square root of both sides and get x. And so x is going to be 0.0952 meters. So 0.0952 meters, plus or minus. You can either compress it or elongate it to store that energy. All right, that's 714. Okay, 7.21, this is very similar to the other one, but we don't have to solve for K. A spring of negligible mass has force constant K equals 1600 newtons per meter. How far must the spring be compressed for 3.20 joules of potential energy? 3.20 joules equals 1/2 times 1600 newtons per meter times x squared, and now we need to solve for x squared. So 2 times 3.20 joules divided by 1600 newtons per meter under the radical is going to give me x. And x is going to be 0.632 meters. So 0.0632 meters. That's x. Okay, now what are we going to do? We want to know you then drop a 1.2 kilogram book on it from a height of 8 meters above 0.8 meters above the top of the spring. Find the maximum distance the spring will be compressed. Okay, so what's going to happen here is the book is going to do work, and the book is going to and the spring's going to stop it. So we've got the book doing mgh, which we have that value, plus mg delta x. That's the amount it's going to push the spring, and that's going to equal to 1/2 k x squared, delta x, right? It's the same x. So we've got a 1/2 kx squared plus mgx plus mgh equals 0. And that's quadratic, where x is the variable. Let's see, what do we have here? Mass of the book. 1.20 kg times 9.8 meters per second squared times how high above it? 0.0800 meters. Oh, that's that last term. Let me just get some board space. This is, no, I'm going to erase. Shouldn't have erased that. Oh, we got that there anyway. Let's go ahead and do this. Okay. I have a 1/2 times 1600 newtons per meter times x squared plus, what was the mass of the book? 1.2 kgs, 1.2 kilograms times 9.8 meters per second squared times x, and that's what the book is going to push the spring, plus 1.2 kgs. Oh, wait a minute, wait a minute. I gotta have a negative somewhere, right? One second. Yes, okay, so I converted that. This guy's got to be negative, right? That's going against the grain. 1.2 kgs times 9.8 meters per second squared times 0.800 meters. And then I just solve for x with do all that math, solve for x. I'm going to pull the solution. Oh, I got to go get the solution. Gonna pull it from, let me get it. And the solution is going to be, let's see, 0.12 meters. That's what the solution manual says. Okay, so X is going to be 0.12 meters. So when you do all that math, and then you can look up a quadratic formula solver online, you'll find X to be that value. And I encourage you to do it. Okay. 7.31 is a calculus problem. It reads, a force parallel to the x-axis on a particle moving along the x. A force acts on a particle moving along the x-axis. The force produces potential energy, U sub x equals ax to the fourth, where a is, okay, so 0.630 joules per meter to the fourth times x to the fourth. What is the force, magnitude, and direction when the particle is at x equals negative 0.8 meters? Okay, so F equals du dx, and that's going to be equal to, is that a negative somewhere? Uh, 4 times 0.630 joules meter to the fourth times x to the third. I did forget that F equals du dx, so right, because if I input a positive force, I'm going to get a negative potential energy, and if I input a negative force going against the grain, then I will have a positive potential energy. So I do need that negative there, right? If I go up against gravity with a negative force, I'm going to increase my potential energy, so you need that. Okay, so then we're going to go ahead and get that value for x negative 4 times 0.630 joules meter to the fourth times negative 0.80 meters quantity cubed. And I'm going to get 1.29 joules per meter, which is equal to 1.29 newtons. This is cubed, sorry. Okay. And that was 731.